How to do a research project. Module 4, Internal Validity and Bias. We are currently on Module 4, Internal Validity and Bias. The learning objective for this module is to describe how to distinguish between internal and external validity and types of bias. There are two critical aspects of external validity. First, scientific generalization is the characteristic of an epidemiological study whereby it may generate a coherent, potentially causal biological hypothesis applicable to a more general set of clinical or epidemiological circumstances than the specific population under investigation. Second, statistical generalization is fundamental in survey sampling in which the resulting sample must be statistically representative of the source or target population. Internal validity is the characteristic of a clinical study to produce valid results. Threats to internal validity are random error, or chance, which can be reduced by increasing sample size, and systematic error, or bias, which cannot be mitigated by increasing sample size. The following figure illustrates the relationship between internal and external validity. Bias can be thought of as the distance an observation is from truth, while precision can be thought of as reproducibility. Imprecision, however, is the lack of reproducibility. Overall, a systematic error in research cannot be fixed by increasing the sample size, for the error will continue to be present and magnified as the sample size increases. In the following figures, each one of the x's can be thought of as a study result. The bullseye and the target is the true exposure-outcome association that we are attempting to estimate, e.g. the true relative risk. The figures can be interpreted as follows. No bias and no imprecision. Results are precise and unbiased. Bias and no imprecision. Results are precise but biased. Note, x's are in great precision and clustered. However, the x's are off of the bullseye. No bias and imprecision. Results are precise and unbiased. Note, x's are unbiased because the average distance from the bullseye is close. Bias and imprecision. Results are imprecise and biased. Note, x's are not in great precision and are not clustered. Bias can be defined as any error resulting from methods used by the investigator to recruit individuals for the study, such as factors affecting study participation, selection bias, or systematic distortions that can occur when collecting information about exposures and diseases, information bias. More generally, bias is any deviation in the collection, analysis, interpretation, and publication of data leading to conclusions that systematically underestimate or overestimate the true relationship between a given exposure and a specific disease or any other outcome. The types of bias are as follows: selection bias, information bias, and confounding. We will now discuss the different kinds of bias to be able to identify and address them. With selection bias, subjects selected for study are systematically different than those not selected. Selection bias is best addressed during the participant selection or recruitment phase of a study. If not addressed then, sophisticated statistical methods will have to be used to try and account for this bias. The following are different types of selection bias. Non-response bias. Non-response bias occurs when non-response is related to the exposure and, independently of exposure, is related to the disease or outcome. Incidence prevalence bias. Incidence prevalence bias occurs when the very sick or very well, or both, are erroneously excluded from a study. Loss to follow-up bias. Loss to follow-up bias occurs when the true relationship between exposure and disease is distorted if the losses during follow-up are selective, i.e. non-random, with respect to both exposure and outcome. The following are additional types of selection bias. Confounding by indication bias. Confounding by indication bias occurs when the indication to treat is a confounder for the treatment-outcome relationship. And volunteer bias. Volunteer bias, or self-selection bias, occurs when individuals who volunteer for a study differ in relevant clinical characteristics from those who do not. In this case, self-selection is a threat to internal validity. In the following example, we will look at how selection bias can drastically affect the findings of a study. Jatoy and Parsons found that contralateral prophylactic mastectomy was associated with reduced non-cancer mortality. This association was stronger than the association between counts per minute, CPM, and breast cancer-specific mortality. They suspect, based on their analyses, that healthier women tend to be referred for CPM more often than unhealthy women. In their study, Jatoy and Parsons found the following. Their hypothesis creates an association between health status and primary exposure, or CPM. Being healthy is independently associated with a lower chance of dying from non-cancer causes. The potential selection bias of selectively referring healthier women with unilateral breast cancer for CPM could account for some of the association between CPM and reduced non-cancer mortality, and, biologically, that CPM should not affect non-cancer mortality so strongly. Overall, the authors suspect that in prior studies that demonstrated an association between CPM and reduced breast cancer-specific mortality, unmeasured confounders rather than CPM itself were likely responsible. Information bias, also known as observational bias or misclassification bias, can be defined as data collection that arises from measurement error. The following are different types of information bias. Non-differential misclassification. Non-differential misclassification occurs with the equal misclassification of exposure between subjects that have or do not have the health outcome, or the equal misclassification of the health outcome between exposed and unexposed subjects. Differential misclassification. Differential misclassification occurs with the unequal misclassification of exposure between subjects that have or do not have the health outcome, or unequal misclassification of the health outcome between exposed and unexposed subjects. Differential misclassification bias is best addressed during the data collection phase of a study by choosing the best possible method to measure primary exposure, e.g. blood pressure, and/or outcome, such as using a high-quality diagnostic test. The following example illustrates how information bias can occur. Clinical research based on blood pressure measurements taken during routine patient care can lead to misleading results unless careful standardization procedures are used. Specifically, multiple studies have shown that correct blood pressure measurement necessitates using appropriated procedures, including using a larger cuff size for overweight and obese adults, positioning the patient so that the upper arm is below the level of the right atrium so the patient does not have to hold up the arm, and taking the measurement in a quiet setting and multiple times. In this case, not using appropriated procedures can skew results, illustrating information bias. Because Module 2.4, Select Potential Confounders, discusses confounding at great length, please refer to this module for a more extended discussion of confounding bias. The following table illustrates the stage of a study where bias can be addressed and how to address that specific type of bias. The next section in this course is Module 5, Designing a Survey. The learning objective for this module is to construct an effective survey that maximizes participant responses.